Yesterday we were discussing about linear congruential generators, which were the first type of stream ciphers. And I told you to remember, stream ciphers are those which work with bits or bytes at a time. So they will generate, and we are talking about pseudo-random number generators, which will generate numbers, random numbers, or numbers which appear like actual random numbers or truly random numbers, but which are actually repeatable after a given period, which means they repeat themselves or the sequence repeats itself after a given length. So, though it is repeatable, it gives you the appearance of randomness because the length after which it is going to repeat is made very, very large. And the first type of pseudo-random number generator which we considered are linear congruential generators. Okay, so we saw a few examples with how to work with linear congruential generators, and I think we discussed about what is overflow. Overflow normally happens when there is an what do you say? There is a carry from the most significant bit. So a given computer has only 32 bits. If we do a multiplication operation, there will surely, most of the times, you can expect a carry out of the 32nd bit, and then we call it as an overflow. And most of the computers will use their MSB bit as the sign bit. So if that MSB bit is 1, it will consider it as a negative number. So the most preferred alternative to work with such cases is to mask the sign bit or mask the most significant bit. So we'll use this pattern 7 followed by all FF to mask the MSB bit. Okay. So with that, what else do we need to know about LCGs? We have a nice table given by the author, that is Bruce Neer. Okay, they all, the sequences given in the table, they all will generate maximal period generators, and they also pass the spectral test for randomness. So we have multiple tests available to check whether a given sequence is random or not. One among them is the spectral test, and this spectral test of randomness is passed by most of these generators, which will be shown in the table. The dimensions of the numbers range from 2, 3, 4, 5, 6, so on. We say, and how are we organizing the table? So that the largest product that will not overflow a given word length. You'll see in this table now. See here, the first column itself tells us where the overflow occurs. So the overflow occurs at 2 power 20. That means till 2 power 19, I'm going to get the sequence. So the sequence is so long, you get an unrepeatable random sequence until I reach the value 2 power 20. At 2 power 20, there is an overflow, and generally we stop at that point. And for that, the A, B, and M values are as shown. You can see here. So remember, how do we define the equation for LCGs? Xn is equal to A into Xn minus 1 plus B, and everything is done modulo M. So this is the defining equation to define the next bit given the present bit, or knowing the previous bit, you can find the present bit. The coefficients A, B is the increment, A is the multiplier, M is the modulus. So all these values have been analyzed and decided, and the author has given us quite a very good table of ready to use LCGs. You can use all these LCGs with the following A, B and M values, and you will get an approximately random sequence which will repeat itself after the point of overflow. So once there is an overflow, we stop at that point. So the highest length, maximal length random sequences are obtained. See, we have shown till 2 power 35, he has specified. Anyway, you can't remember this table. This is only to show that we have ready to use material available if you want to work with LCGs anywhere. Now, let's move on to discuss effectiveness of LCGs. LCGs can't be used for cryptography for the simple reason that they are very predictable. We have a simple equation and we can easily determine the next number of the sequence. You can easily predict the next number in the sequence following that equation. And even if you don't know few things, there are many people like Joan Boyer and Jim Reeds who worked on how to break these LCGs. So the first LCGs were broken by them, and later on they tried to use quadratic generators. What are quadratic generators? Equations in the form ax square plus bx plus c. So the first set of LCGs were linear generators, right? Here we have ax n minus 1 plus b mod m. So this is linear. But here, if I say ax minus 1 square plus bx minus 1 plus c, this is a quadratic equation. It is in the form of x a square plus 2ab plus b square, quadratic equations, right? So they designed quadratic generators, assuming this will be a little more complex to break. But Joan Boyer also broke these quadratic generators, which are in this form. Then they went to cubic generators, the cubic generators which are in the form a x minus 1 cube plus b x minus 1 square plus c x minus 1 plus d mod m. Even these cubic generators were broken. In general, there were many researchers who extended this Joan Boyer's work to break any polynomial congruential generator. So whatever complexity they added in the polynomial generating function to generate the next number given the present random number. So they used quadratic equation, they used cubic equation, or in general any other polynomial generator. Everything could be broken easily. So LCGs as such, they remain useful for non-cryptographic applications. So they are not preferable with cryptographic application because they are highly predictable and they are easily breakable. People can break these LCGs very easily and you get predictable random numbers also. Though you work with large values of A, B and X naught. You remember what is X naught? In LCGs, what is X naught? Remember, this is another parameter which we spoke of. Can someone tell me? Yes? What was X naught in LCGs? You knew what is XN?
Initial seed.
It is the initial seed value. Please remember the terms. X naught was considered as the representation for the initial seed value. So this is supposed to be the starting value or the seed value which we specified. Okay.
Ma'am, that's the old message, ma'am.
Pardon?
Ma'am, like you replied that, that's the old message in WhatsApp. Hello?
In WhatsApp?
Yeah, ma'am. Like you said, give me a minute. Like that's old mess. I joined the class.
Okay, okay, fine. So here, this is about LCGs. So please remember, LCGs are not preferable for cryptographic applications because of their predictability and because of their simplicity in uh, breaking the cipher. Okay, if I use this for any cipher, then you can easily break the cipher. Okay, but they are helpful in many other places in simulations also, and they are very efficient. They give good statistical behavior, and they pass many of the randomness tests. So coming to the good properties of LCGs, they have maximal sequence length, which is m minus 1, so which is quite good. So the maximal sequence length is large, and they pass many tests for pseudo randomness or randomness. Bad properties, as we said, they are predictable. Even polynomial congruential generators were broken very easily in the early 80s itself. So 70s, 80s itself, they discarded the use of LCGs for cryptography. And before leaving LCGs, we also want to discuss how to select the seed value. The initial seed value, or X naught, what we call as. How do we normally select when we use it in simple educational applications? So to select the seed value, we try to add some randomness. You look at this, these two expressions shown below. This X naught or the seed value is determined by the current year. I year stands for the current year. Say the current year is 2022 plus 100 into the current month. The current month is the first month, January, minus 1 plus 12 into the current day. The current day is 7 minus 1 plus 31 into the current hour, which is 12 plus 24 into the current minute, maybe the 20th minute, and 60 into the current second, maybe I'll say the 55th second or so on. So this is a simple example of how we can select the seed value based on some random parameters. So whenever I'm trying to use it, I'll use the current year, current month, and so on, and I'll try to find the seed value. This can also be put in the other order. We'll put the year in the innermost brackets, then the month, then the day, then the hour, minute, second. The second is outermost. So we are reversing this. Here we have taken year as the outermost. In this, year is the innermost. So we could, these are just some examples of how you can select the seed value so that it will be something random. Okay. I hope you got it. You please stop me if you feel I'm going fast or you don't understand anything. Because unless you tell me, I'll not know. And preferably, please do it orally because checking messages constantly would be difficult. Okay. So let's proceed. Characteristics of good LCGs, or which act like pseudo random number generators. So generally, as I told you, a large value of A is desirable to give you proper randomness. A large value of M is also desired so that okay. Okay, so whenever you have to write down few things, Then I'll go slowly in those slides. The other slides which are major theory, I think I'll go a bit fast because anyhow I'm going to pass on the slides. Okay. You can make notes, short notes, something important. So large value of M is needed, large value of A is needed. All these will keep the period long. The repeatable period will be kept long because of that. Okay. So what are the salient features of LCGs? Multiplicative congruential generators are in the range adequate to good for many applications, but they are not preferable for high dimensional work like cryptographic applications. Okay. And especially they are used in such applications where speed is a major concern. Okay. Wherever I want good speed, fast generators, in such applications, these LCGs are commonly used, but prime modulo LCGs, when I use modulo to a prime number, they are the best usually. But even we use modulo 2 power m because they are faster on binary computers. So when I use a modulo in the form of 2 power m, even that would give you fast results on a binary computer. Okay. So this is about salient features of LCGs. Then people also tried combining LCGs to get longer length periods. So that repeatability was pushed to much longer lengths by combining two LCGs. Okay. So they examined the combinational of LCGs and they saw that the results are not cryptographically secure. It won't help us to use them in cryptography, but combinations will generate longer time periods or longer periods and they perform better in many randomness tests. One example is say the LCG with with a period 2 power 31 minus 85 is combined with another LCG with a period 2 power 31 minus 249 and the product of both, the combination of both will have a period which will extend from minus 2 power 31 plus 85 to plus 2 power 31 minus 85. So it will give you a much longer time period, almost double the time period which was given by the individual generator. This individual generator gave only plus 2 power 31 minus 85. But this ranges from minus 2 power 31 plus 85 to plus 2 power 31 minus 85, which is quite huge, almost double that value. So all these numbers may not be easy to remember and you are not expected to remember everything. You can just write in general. So you can just say in general it can increase the period of the generator. A single generator will have shorter period when compared to a combinational LCGs. So the generator has a period somewhere in the neighborhood of 10 power 18, which is huge. With this, we complete LCGs or linear congruential generators. And let's move on to the next type of stream ciphers or next type of, actually what we are discussing are the basic blocks which will be used in actual stream ciphers. We are going to see some examples of actual stream ciphers a little later. So these LCGs and next the LFSRs, the linear feedback shift registers, are basic building blocks of the stream ciphers. So we are analyzing these building blocks first. Is that clear? So what is an LFSR? A linear feedback shift register, we are very familiar. You have used it in ITC, right? In cyclic codes, remember in ITC cyclic codes, the generator and both encoder and decoder are nothing but feedback shift registers. They are nothing but linear feedback shift registers which you have used. You have used a shift register and the flip-flops are separated in between with XOR gates to determine the next state, so on. And there is always a feedback coming in the form of an AND gate, and from that there is feedback coming to different points, the different modulo 2 adders. So whatever you did with cyclic code, encoder and decoder, they are the simplest examples of LFSRs. Here we will be studying some more types of LFSRs and how they work. So shift register sequences are very useful in cryptography as well as coding theory. And stream ciphers based on shift registers have been considered as the workhorse of military cryptography since the beginning of electronics. What do you understand by this sentence? What do you mean by workhorse? What's a workhorse? Yes?
Like something that is continuously used.
Exactly, something which is used more for work. It can even be a work donkey, where here why we call it as a workhorse. People used to use horses for work often, mules or something, and they would make them do lots of work. So this LFSRs have been used extensively in military cryptography from very early days. And the simple equation which defines an LFSR is something like this. Say the bit xn plus m can be obtained as C0 into xn plus C1 into xn plus 1, so on, plus Cm minus 1 into xn plus m minus 1. So here, I'll come to these equations a little later. We'll just do the basics. LFSRs are supposed to be very fast in hardware and a little slow in software. When compared to hardware realizations, software realizations are a bit slow, except in Cray computers or Cray machines, where there are some instructions called as population count instruction. So pop count, they call that as. Once that instruction is used, very easily it gives the number of ones and zeros. It's a very useful instruction which can be used. So coming to the linear feedback shift register, basically it will have two parts. The first one is a shift register and then a feedback function. So usually you'll have something like this. You'll have a shift register here with multiple flip-flops, and then there is always a feedback function. That feedback function will initiate some inputs from the shift register. It will take some inputs from the shift register and it will generate an output which will be fed back to one of the bits in the shift register. So I can have the feedback coming to the MSB bit position or the LSB bit position, and the other side would be the output. So remember, the output should come in bits. So one side it will take the feedback, the other side it would generate an output. So two parts basically. So usually we know what's a shift register. It is a sequence of bits. Length of shift register is always given in terms of bits. So if I say I'm using an n-bit shift register, it has n flip-flops to store n bits at a time. Each time a bit is needed, all of the bits in the shift register will be shifted once to the right. So in this case, we are taking the output at the right. All bits will be shifted right by 1 bit. The new leftmost bit is computed as a function of other bits in the register. So we are defining a feedback function, and that feedback function will be making use of some input bits from the shift register, and it will help you in deciding what should be the leftmost bit. Okay, what should be the leftmost bit. And output of shift register is 1 bit and often the least significant bit, but that's not always the case, remember. Usually the LSB bit will be the output, but always it is not true. And the period of a shift register is the length of the output sequence before it starts repeating. Just like how we considered in LCGs, here also the period of the shift register will be what is the highest length of the output which I am getting until it starts repeating. Non-repeating output bits, if I get say 16 non-repeating output bits, 16 will be the length of the sequence. Okay, the output sequence length, output random sequence. Remember, all these are supposed to be generating random output sequences. So we are using LFSRs to generate random output sequence. In this diagram, you can clearly see how an LFSR looks. As I told you, the bits in the shift register, what is shown in blue here is the shift register. We are starting with bit xn, xn plus 1, xn plus 2, so on till xn plus 7. So we have 7 bits in this shift register. I am using xn plus 6, xn plus 5 and xn plus 4 as inputs, and I am using 3 modulo 2 adders. See, xn and xn plus 4 are the inputs to the first modulo 2 adder. The output of the first modulo 2 adder and xn plus 5 are the inputs to the second, so on. Finally, the output of the third modulo 2 adder will be given as the input to the what? Xn plus 7 bit, the leftmost bit. So all this tells us the realization of the feedback function. And these are the bits in the shift register. So the two parts of the LFSR, that is the shift register with n flip-flops and the feedback function, which is normally realized using modulo 2 or adders or XOR gates. So they are simple XOR gates. Modulo 2 addition is nothing but XOR operation only. Yes or no? So all of you remember modulo 2 addition is same as XOR operation. So you can see the defining equation what we wrote there, the same defining equation. So what do you think the C0, C1, Cn minus 1, all these will represent? Anybody? They are just the coefficients which will be in the form of ones or zeros. So if a given bit has to be included, it will be a 1. If the given bit is not there, it will be a 0. So the feedback function is defined like this. How to compute the bit xn plus n? It is by adding certain bits in the shift register. And the addition of those certain bits depends upon these coefficients C0, C1, so on. So if at all those bits are ones, then that particular bit is considered in the addition. If they are zeros, it is not considered. So here you have an option of using multiple 2 input XOR gates, or you can also use a single XOR gate with all the inputs connected to the same gate. It can be a 4 input XOR gate where I can put xn plus 6, xn plus 5, xn plus 4 and xn. So all this can be connected as inputs and the output can be connected to xn plus 7. This can be used like this or like this, both are correct. The realization in hardware. So the simplest kind of feedback shift register is a linear feedback shift register. The feedback function is generally the XOR of certain bits in the register. List of these bits is generally called as tap sequence. So which bits we are using as input, we call that list as a tap sequence. What we have shown here is also called commonly as the Fibonacci configuration. Okay, we have two configurations for shift registers or LFSRs. We have the Fibonacci configuration and the Galois configuration. So we'll be studying the two configurations here. The one which is shown in this diagram is a Fibonacci configuration. So because of the simple feedback sequence, large body of mathematical theory can be applied to LFSRs, and cryptographers surely like to analyze sequences and convince themselves that they are good enough or the randomness is sufficient to be secure. And the most common type of shift registers used in cryptography are LFSRs, as I told you. And there are some important properties for LFSRs. So, as I told you, the coefficient key is also, it's also called as key, C0, Cm minus 1, and the starting sequence is important. So, n-bit LFSR can be in one of the 2 power n minus 1 internal states. Remember, if I am using a shift register of n bits, I'll get 2 power n total combinations. Yes or no? If you have a shift register of n bits, 1, 2 to n, so total number of possible combinations will be 2 power n. And why I am going to consider 2 power n minus 1? Because if you remember, to compute the feedback function, we are using XOR gates. Which combination should be avoided in an XOR operation? Which combination do you think will result in the same value always? For an XOR gate, if all its inputs are zeros, the output will constantly remain a zero. So it can never come out of that configuration easily. So that all zero state. So the all zero state is avoided here. Remember, if at all the shift register enters the all zero state, there is no chance that we can come out of this state using this XOR operation, right? So out of 2 power n combinations, I'm going to leave out the all zero combinations. That's why we are telling it has a possibility of 2 power n minus 1 internal states. Okay. And in theory, it can generate a 2 power n minus 1 bit long pseudo random sequence before repeating. So the maximum possible length of the random sequence, remember the output is taken here. The output random sequence, the binary sequence which it will generate, will also have a highest length of 2 power n minus 1, which is possible. Okay. And LFSRs with certain tap sequences will give you maximal length sequence. It will cycle through all the possible internal state and it will result in maximal length or maximal period outputs, but not all LFSRs. If I choose the tap sequences, what is tap sequence? Those bits which should be input to the XOR gate or the feedback function. If you are able to choose this tap sequence correctly, only certain tap sequences result in maximal length LFSR. Just like how we had certain values of A, B and N could result in maximal length LCG. Just like that, here only certain length, certain tap sequences will result in highest length LFSR. So in order for a particular LFSR to be maximal period, the polynomial formed from the tap sequence plus the constant 1 should be a primitive polynomial modulo 2. What is the meaning of this? The degree of the polynomial is the length of the shift register. The primitive polynomial of degree n should be an irreducible polynomial which divides x to the power of 2n minus 1 plus 1, but it should not divide x bar d plus 1 for any d that divides 2 power n minus 1. All these are, let's say, a little bit complex technical jargon, but you need not worry much because we are not going to look into the details of how to choose the polynomials. We are already given certain polynomials. We'll be checking, our intention here is to learn how to use the LFSR, not to find how to find the generator or the primitive polynomial for the LFSR. Okay. Every LFSR is defined by that polynomial, which is nothing but the feedback function. So the polynomial which we are talking of here is the feedback function which we are going to define. Okay. So in general, as I was telling you, there is no easy way to generate the primitive polynomials mod 2 for a given degree. So the easiest way is to choose a random polynomial and just test whether it is primitive. So that primitive testing is based on this second point. When do I know whether it is primitive? Because if I take a polynomial of degree n and I have it as an irreducible polynomial, when it should divide this, but it should not divide x bar d plus 1 where d divides this. So this is a condition which should be satisfied. As I told you, this is complicated. It's like something for testing like random numbers for primality, whether a given number is prime or not. But there are many software packages which can do this easily. So people have written lots of code to find these irreducible polynomials or to find the primitive polynomials modulo 2, which can be used to generate maximal period LFSRs. Okay. So maximal period LFSRs can be easily generated by choosing a particular polynomial using some software package. We'll not try this division and all that. See, for example, it will be listed like this: 32, 7, 5, 3, 2, 1, 0. It means that the polynomial will be defined like this: x bar 32 plus x bar 7 plus x bar 5. So whatever values are listed here, that should be powers of x. And whether we mention 0 or not, this plus 1 is always there. Please remember, this is compulsory. Plus 1 should always be there whether you mention 0 or not. So it's easy to turn this into a maximal period LFSR. The first number is the length of the LFSR. So this 32 will also specify what will be the length of the LFSR. Last number is always 0 and it can be ignored, as I told you. All the numbers except the 0 here, all these numbers will specify the tap sequence. This is what we call as the tap sequence for the. So the tap sequence will be specified like this. And the primitive polynomial modulo 2 is given like this. Okay. So if I have to turn this into a maximal length LFSR, it is very easy in terms that the last value will always be 0 and all other numbers except 0 will specify the tap sequence counting from the left of the shift register. So low degree terms in the polynomial correspond to taps near the left hand side of the register. For example, how are we going to draw this? Say I want to use this as the tap sequence and construct a Fibonacci shift register. How will it look? So let me say this is the shift register and I'll start with 1, 2, 3 from the left hand side and 32, the 32nd bit. Remember, the highest length of the shift register is 32 bits. So start with bit number 1 from the left and go up to 32. Or if you consider this as 0, this will range till 31. Okay. And now the feedback function, how you are going to define. I told you, you can either use a single XOR operation or single modulo 2 adder, or you can use multiple 2 input modulo 2 adders. Now tell me what should be the inputs to this adder. Let me use a single one to simplify the job. The 32nd bit should be the input. I told you this forms the tap sequence. Then the 7th bit should be the input, right? Then the 5th bit. So I should have the 5th bit also connected as input. The 3rd one, 2nd one, and 1st one. All this are inputs. So all these together will be inputs to the modulo 2 adder, and the output of this adder will be connected to the leftmost bit, and the final output is read from the rightmost. The output of the LFSR is taken from the rightmost bit, and the feedback is given to the leftmost bit. And remember, every time a feedback is generated, there will be one right shift. Okay. So as you can read here, you can see you take a 32-bit shift register and generate the new bit. The new bit comes in this position, the new bit, by XORing the 32nd, 7th, 5th, 3rd, 2nd and 1st bits together. And once you do that XOR operation, what should you do? You have to shift. So the last bit is generated in the leftmost bit position and the rightmost bit is taken as output. There is a shift happening. This is how we realize the LFSR. And they have also given how you can write the C code. A simple code in C for an LFSR. It's very, very easy. So let me consider int LFSR as a function. Okay, I have defined the function. Anyhow, it will have only integer values. Now, in that function, I am defining a variable shift register. So this shift register should be equal to, you see, which bits should I take as input? The 32nd bit. So since I am starting with 0, I'll consider this is the 32nd bit. This is the 7th bit. Okay. Remember, we are given 32, 7, 5, 3, 2, 1, right? So this is the 5th bit, this is the 3rd bit, this is the 2nd bit, and this is the 1st bit. Just shift register without any shift. So we are just doing an XOR operation. XOR all these bits, and once you have XORed all the bits, you perform an AND operation with the least significant bit being 1. So you are checking whether the least significant bit is a 1. Okay. So you remember. So please remember, I don't know why all of you are entering your USNs without me telling. I've told you multiple times. So people want to just enter your USNs and leave. You can leave. I don't know, attending online classes also is difficult for you, offline classes also. Your seminar and project marks, internship, all depend on your attendance. At least with online, you could have made up for the attendance, but people are taking it lightly. I don't know what. And so here, as I told you, then we are masking it by performing an AND operation and checking the rightmost bit. And after that, we will be taking the value and shifting. That value will be shifted to the 31st bit position or the what? This position. Remember, this was your 31st or 32nd position. This was your 0th. So whatever value you get, here when we have done the XOR operation of everything, we have done the XOR operation by taking all these inputs. Whatever output we are getting, that bit we are considering. I want a single bit, that's why I do an AND operation. So I just want the single bit which is now in the rightmost position. Okay, because if that single bit is a 0, the result of AND operation would be a 0. If the output of the XOR was a 1, the result after AND operation would be a 1. Now where should I bring this bit? This bit should be brought to this 31st bit position or the leftmost position. That's why we are left shifting by 31 bits. So whatever 1 we have in the rightmost position, I have something like this 0, 0, 0, 1 here. This should be shifted and brought to the 31st bit position, the leftmost bit position. That's what we are doing here. After doing that, we will again we'll perform an OR operation to what? Add this back. So I have brought the feedback bit and I have put it here. After that, whatever was the content of the shift register, the previous content, say I had something like 10, 10, 111 something, that content is added back. Okay, and once we do that, we'll do a right shift by 1 bit, telling we are taking out the first bit outside. After every feedback which is generated, a right shift should happen. So whatever shift register contents were there, I'll show you in the example when we do it next. So the shift register content, say, was something like this, and we have XORed these 3 bits, for example. So 0 XOR 1 XOR 1, the output is a 0, right? So what should happen in the next clock cycle? This 0 should come and sit here, and everything should move right by 1 bit. That's what we are doing. The old contents of the shift register is shifted right once. So we shift the old contents of the shift register right once. That means 1, here I am going to have 1 0 1 0 0, and this 1 comes out. So when this is the value, that will be ORed with this MSB bit position, so that you will get the final version, shifted version in the shift register. I hope you are following this. It's a very simple code which we are realizing. And when we do the corresponding example problem, you can see it easily. As I have shown you here, take the corresponding bits which is mentioned here, perform an XOR operation, and whatever XOR value, that XOR value will be what? Retained in this LSB position, and that's why we are masking the other bits. If there were any non-zero values here, we are masking, and whatever was the result of XOR, that should come and sit in the leftmost position. So we are doing a left shift by 31 bits. So once it comes to this position, whether it was a 1, the result of XOR, or 0, that is there, and there are zeros in the other position. Now, to this value, I should have the previous contents of the shift register, which was shifted right once. So, because I am filling in the leftmost position, the previous content of the shift register has been shifted right once. So, here I had 1 0 1 0 0 1. So, that has shifted right once, 1 0 1 0 0 1. So, a single 1 has gone out. This is the new content of the shift register. This is the result of the feedback. Now we are performing an OR operation on these two. You see, this is an OR operation, and you will get the final shifted result. Whatever is the shifted result that is obtained. Okay. So this is how we realize. This is a simple example of a 4-bit LFSR. You can have a look at this and you can see how the states are generated. The tap sequence used shows only the rightmost bit and the leftmost bit. So this is 1, 2, 3, 4. You see bit 4 and bit 1 are used, and the feedback is coming here from the XOR gate, and this is the output. So you can just see the sequences. If the initial value is also important. Say I had initialized this with all ones. Can you write the next numbers in the sequence? So this will be 1 XOR 1, which is a 0. So the next number in the sequence will be 0 in the leftmost position, and the bits should be right shifted 1. So 0, 1, 1, 1. And after that, what would be the value after that? So in the next part, you will have 0, 1, 1, 1, and you are adding the last two bits. So 0 XOR 1 will result in a 1. So what will be the next value? This 1 should come here and everything should shift right by 1 bit. So the next value will be 1, 0, 1, 1. You can see the next state is 1, 0, 1, 1. Next you start with 1, 0, 1, 1. XOR the last two bits. You will get 1 XOR 1 is a 0. Bring this 0 to this position. Shift everything right once. So you will have 0, 1, 0, 1. This one goes out. So the next state is 0, 1, 0, 1 in the shift register. Likewise, if you go on continuing, you will get 16 states, and it will all of which are different. It's generating a maximal length sequence, and the output is taken. What will be the output sequence here? Whatever is there in the LSB column. So whatever is there in this last column, that will be coming as your output sequence. So initially the first bit which comes out is 1, the next bit will be 1, 1, 1. So this would be the output sequence which you will see at the output of this LFSR. Okay, so this is how LFSRs are realized. We'll see the two types and we will see how to work out the problems with these LFSRs in tomorrow's class.